Hello and welcome back to Calculus, the series where we explore integrals. First and foremost, I'd like to thank all the nice people that support this channel by liking and subscribing. Today, I'd like to begin exploring the different ways that we can integrate more complicated functions, where the basic integration rules that we have covered in the past 3 parts just won't be enough. The technique we will begin learning today is called integration by substitution. The idea is the following. Functions that require some of these advanced integration techniques are almost always composite functions. So, in order to make our life easier, we use something called the U substitution. The concept is this. Suppose we're integrating a composite function in the form of f of g of x. What we do is introduce a variable u and set it as equal to g of x, the function on the inside. So technically now we're doing the integral of f of u. And then after we find the antiderivative function, we'll get the big f of u plus c. And then we take the substitution we made and plug it back in. It seems simple enough. However, there is another step in the middle where we do have to calculate the derivative of u in order to get a more accurate answer. Why that is necessary, I would like to show you with an example. Let's say we're asked to compute the integral 3 times the integral of 6x minus 1 times e to the power of 3x squared minus x. This is a pretty complicated function, and simple integration rules will not help us here. So, step number 1, we would introduce a substitution, the green part. U is going to be equal to the power. So in this case, that would be the 3x squared minus x. Next up, what I want to do is the derivative of u. So I write it as du dx, and this is going to be equal to 6x minus 1. Note that this answer comes from differentiation rules. Well, mainly the power rule for differentiation. And then, since du dx is just a fraction, I can actually write du is equal to 6x minus 1 times dx. All I did was multiply dx by both sides of the equation. Now, after computing this derivative, you might have noticed something. Our du is equal to 6x minus 1 dx. Now, if we look at our original function that we were asked to integrate, we also have 6x minus 1 times dx. So that means in the revised integral, I can first write e to the power of u, and then I can simply replace 6x minus 1 times dx with just du. This derivative here was necessary to compute because when we introduce a new variable u in our substitution, that means we have to also integrate our function with respect to the variable u and not x anymore. So this means we need to switch from dx to du, and computing the derivative is going to help us achieve just that. So now that we have a simplified version of our integral, we can simply compute this. We know that e never changes, no matter if you do the derivative or the integral. It's still going to be just e to the power of u. And of course, never forget that we had a constant in the front. And in the end, we do have to add a plus c. And then, in the final step of getting our answer, all we have to do is plug u back into the substitution we originally took it with. So, u is equal to 3x squared minus x. And this right here would be the answer to our integral. It doesn't seem that difficult. So, let's take a look at another example. However, before we do that, I'd like to go over a few basic rules of integration. They're called integration by inspection, or in other words, they're basically formulas that you have to remember in order to compute integrals effectively and correctly. As mentioned above, whenever we integrate or differentiate the function e to the power of x, it never changes. Integral of ex is still going to be ex, of course, plus c in the end. Next up, we have the integral of 1 over x. Here, the answer is going to be ln modulus of x, and of course, plus c. Why we add the modulus is because originally, in the fraction, x can be negative. However, after you do the integral, when you put the x into the natural log, it must be positive, or in other words, greater than 0, because of the domain of the logarithmic function. We cannot take the logarithm of negative numbers or 0. Next up is a subpoint. So when you compute the integral of 1 over ax plus b, this kind of format, what you get is also going to be the natural log and absolute value of ax plus b plus c. However, there is one thing I would like for you to pay attention to. In this case of a fraction, the bottom part must be linear. It must be linear in order for this integral to be equal to ln. If in the bottom you have, for example, 1 over x squared plus x, and you compute this integral, please note that this is not going to be equal to the natural log of x squared plus x and plus c and so on. The bottom part must be linear. And of course, don't forget, this is the composite function. So we have to divide by a, which is the derivative of our linear function. Next up, when you integrate a function in the form of a to the power of x, the integral you're going to get is a to the power of x over ln of a, and of course, plus c. And finally, we have one quite special rule. If you can clearly notice that you are integrating a function, a fractional function, and in the denominator you have the function itself, and in the numerator it's the derivative of our denominator, you can immediately know that the integral here is going to be the natural log of f of x, and of course, plus c. And of course, finally, we do have some trigonometric integrals that have already been mentioned before, but I will write them down just as a reminder. Okay, so now that we know this, let's take a look at another example for integration by substitution. Now we're going to be integrating the function cotangent of x. Of course, I did mention that majority of the functions we integrate by substitution or by any other more complicated technique that will be done in the future are mostly composite function, but it doesn't always apply everywhere. So step number 1 here will be to rewrite the cotangent. We know that tangent itself is sine over cosine, so cotangent is going to be the reciprocal function, cosine over sine. And now what we can do here is actually substitute the bottom part, sine of x, put it as u. So when you do du dx, or the derivative of u, you're going to get cosine of x. And this just means that du is going to be equal to cosine of x dx. Once again, I want you to look at du. It's equal to cosine of x dx, and now take a look at the original function we were asked to integrate. On the top here, we also have cosine of x and dx. It means we can simply replace it with du. So the simplified integral is going to be the integral of 1 over u du. And now this integral can be computed by inspection, because we know that when we have the integral of 1 over u, or 1 over x, the integral is going to be the natural log of x. In this case, it is going to be the natural log of u and plus c. And of course, for the final answer, all we have to do is plug u back in. So u was originally sine of x, so that's exactly what we write. And our final answer is the natural log of sine x plus c. So today, we will end here with the basics of integration by substitution. In the next video, I would like to go over the more difficult substitutions, especially in cases where you evaluate the derivative of u and it doesn't fully take away dx and the rest of the complicated function. So we'll look into that in the future 1 or 2 parts. So I hope to see you there and have a nice day. Bye.